Good morning, ladies and gentlemen. Today we're going to start a new unit. Today we're going to start finally talking about the mole. You may have heard me use the term in class before, and now we're going to start learning what it represents and how we utilize it. Okay? First, we're going to begin with a scientist named Avogadro. Avogadro developed what we call Avogadro's number. Okay? What does that number represent? Okay? We're going to get there. I would like first to start with this because this will help you understand the rest of this a lot more. A mole is just a quantity. The word itself represents a number. What do I mean by that? A dozen, if you hear the word dozen, what does dozen mean? Dozen means 12. Dozen itself represents a value. That value is 12. Okay? If you have a baker's dozen, you have what? 13, if I recall. Okay? The word itself represents a number. So if you have a mole of something, you have a specific amount of something. Okay, and we're going to learn what that number is. And that number is tied to Avogadro's number. Okay, so remember, all elements, all formulas, all compounds, they have a specific mass. Okay, and when we're talking about atom size, okay, on the atomic scale, we have to use AMU. Okay, so on the periodic table, you know that the number at the bottom is what tells you how much that atom or element weighs, right? But it is specifically in AMU. So oxygen, you can round that to 16. Oxygen, one oxygen atom would be 16 AMU. One helium atom would be 4 AMU. One hydrogen atom would be 1 AMU. Okay, AMU just tells you that we're talking about the atomic scale. Okay, so one single atom is AMU. So if we have carbon, carbon would weigh, one carbon atom would be 12 AMU. If you wanted to convert that to grams, carbon, one single carbon atom, which has 12 AMU, would be about 2 times 10 to the negative 23 grams. Okay, so one single carbon atom weighs very, very, very little, or the mass is very, very, very small, and that makes sense. It's one single atom. So, at what point or how many atoms of something do we need before it starts to become tangible? Okay, this is where Avogadro's number comes in. Okay, so let's say we're working with hydrogen. Okay, let's say we're working with hydrogen. Hydrogen has an atomic mass of 1 AMU. And let's say I thought to myself, how many hydrogen atoms would it take for me to get 1 gram? The same as the atomic mass, but instead of AMU, now we're in grams. How many atoms do I need to get 1 gram of hydrogen? It turns out you need Avogadro's number worth of atoms in order to get 1 gram of hydrogen or 1 mole. Okay, this is where the mole comes in. So hydrogen has a mass of 1 AMU. Right? We got that from the P table. How many atoms would it take to make 1 gram? You need this amount. Okay. And this number, that should be times 10 to the 23. And I'm going to rewrite it. So this number is called Avogadro's number. And it's 6.02 times 10 to the 23. Okay. And if you have Avogadro's number worth of atoms or a single mole, so this 6.02 times 10 to the 23, this is 1 mole. Okay. So this is what a mole represents. So now you know what a mole is. So 1 mole is this many. Okay. That's what a mole represents. That's all it is. 1 mole is this many. But this number is special because it gives you the exact amount of atoms you need to convert the periodic table mass to grams. Okay. So if you have 1 mole of hydrogen, you have 1 gram of it. If you have 1 mole of oxygen, you now have 16 grams of it because the atomic mass is 16. Okay, if you have 1 mole of nitrogen, you have 14 grams of it. So what it does is converts that AMU to grams. Okay, it's how many atoms you need to get the AMU value in grams. Okay, 1 mole of helium would give me 4 grams of helium. Okay, so you have the same number of atoms in all of them. So 1 mole of hydrogen and 1 mole of helium, it's the same number of atoms, but because helium has more particles in it, it's going to be a little heavier. Okay. Because remember that mass has to do with the number of protons and the number of neutrons. So the more protons and neutrons you have, the heavier the atom is going to be. Okay. But 1 mole converts that periodic table mass into grams. Okay. Here's an example. How did we determine this number? Okay. So where does number come from? How do we calculate it? With simple algebraic equation. If you know how much one atom of something weighs, so in this case we have carbon. So one carbon atom, one single carbon atom weighs this many. Okay. And we want to know how many atoms we need to get to 12.01 grams, which is the atomic mass of carbon. You do some calculations to get this by itself. We're solving for the question mark. You got to divide by 2 times 10 to the 23. You do that, and out pops out Avogadro's number. And if you were to do this with any other element, you would get the exact same number. Okay. So if you wanted to instead do oxygen, we would change this to 16, and we'd have to find how much one oxygen atom weighs. And you do the calculation again, you're going to come out with this number every single time. Okay. So 1 mole of something is equal to this many atoms, which gives you the periodic table mass in gram form. Okay. I'm gonna skip this section. All this is just they're trying to give you a scale. So 1 mole, how big is that number? 6.02 times 10 to the 23. How big is that number? Well, if you had 1 mole worth of marbles, you would cover the entire Earth 2 miles deep. Okay, this is just they're trying to give you a scale of just how big that number is. Okay, if you were to start from 1 and count all the way up, it would take you 20 billion years, even if you were doing a million numbers a second. Okay, that's all. They're just trying to give you a sense of scale. This is what I was talking about. A mole is just a quantity. Dozen is another example. A dozen is 12. 1 gross of something is 144. A ream is, I'll Google it for you so you can see. A ream is the paper. The stacks of paper, this is 1 ream. So if I have this, that means I have 1 ream of paper. And 1 ream is 500. Okay? And a mole is just a number. The 1 mole is 6.02 times 10 to the 23. Okay? So that's the part I need you to get into your head. All a mole is, it's just a value. A mole is just a number, and that number is 6.02 times 10 to the 23. That number is special because if you have that number of atoms, you have the atomic mass in gram form, okay? And that applies to formulas as well, and we'll get there in a second, okay? And now I just want us to practice doing some calculations, applying these. Okay, so now we're going to apply these groupings. I'm going to breeze through this real quick. So if we have 2 dozen eggs, how many eggs do we have? 1 dozen is 12, so 2 dozen would be 24. Okay, here's B. If you have half a dozen, that means you have half a 12. Half a 12 is 6, so 2 would be C. Okay, now we're going to start using the actual mole value. So how many particles of sand are in 0.5 moles of sand? So we have 0.5 is half. So we have half a mole. So to get half a mole, you just take the mole, 6.02 times 10 to the 23, and you divide that by 2. So 6.02 divided by 2, you're going to get this. Okay, put that in your calculator. That's what you're going to get. How many pieces of gold dust are in 2 moles of gold dust? So instead of 1 mole, we have 2 moles. So, it's an ugly 2. And so then all we need to do is multiply this number over here by 2. And if you do that, you get this. Okay. So this is D. So just take the mole value and just multiply it by 2. If you have 2 dozen, you multiply 12 by 2. It's the same thing here. So 1 mole, but we have 2 of them, so you got to double it. So put that in your calculator, multiply it by 2, and you get D. How many dozen eggs are in a container of 6? So now we're going from a regular number to the dozen. So if you want to work this way, just start off with what you have. So 1 dozen is 12. Okay. We know 1 dozen is 12, but we don't have 12. We have 6. So 6, 12, 0.5. This one would be B. This, a dozen again is 12. We don't have 12. We have 18. So you would do 18 divided by 12. And you should get 1.5. Okay, I'm going through this kind of fast because this is simple math. The dozen stuff for the mole, I'll go a little slower. Okay, and this will be the last one I do before I move on to the next section. The Milky Way galaxy has 400 billion stars. How many moles of stars is this? So they give you the number. We have this many stars. How many moles is it? Well, 1 mole is this. So to find out how many moles of it do we have, just how we were doing with the dozen, you need to take how many of it you have. And divide it by how many is in 1 mole. In 1 mole, you have this. And if you put that into your calculator, you get a value. And what is that value? I will find out for you right now. Divide that. Oopsie. Take this number and divide it by 2 times 10 to the power 23, and you get B. Okay? And more examples of the same thing. Now we're going to continue on with the next piece. So again, if you have 1 mole of something, you have its periodic table mass in gram form. Okay, so this is what 1 mole of carbon would look like. Now, instead of the atomic form, now we can start to see the real what it feels like, tangible. Like now we have an actual something we can see. Okay, so this is the atomic scale, and then this is a worldly scale, something we can actually see and touch. Okay. So this is the formula that you need to find out how many moles of something you have. Just like a dozen, if you want to find out how many moles you have, you need to know how many of it you have and divide it by Avogadro's number. Okay. So n, the little n, this little n is moles. Okay. The big N is number of atoms or particles. Okay. And then Na is Avogadro's number. And this is exactly what we just did in the examples above. Okay, I don't know why I'm writing it out because it's here as well. And Na is Avogadro's number. Okay. So this formula, we just eat without us writing anything or seeing it before. That's exactly what we just did here. Okay. We have this many number of stars. 1 mole is this amount. You divide them together and you find out how many moles you have. This formula is exactly what we just did. We just used it. We didn't know it was written like this, but this is exactly what we just did. Okay. And this is what you're going to be applying to today's work. You're going to be trying to figure out how many moles of something you have. You're going to go from moles to particles and particles to moles. Okay, that's what this formula is used for. It's to go between particles and moles. So here's an example. How many moles of gold are there in a sample containing this amount of gold? So looking at the formula above, moles is equal to, so little n is what we're looking for. N is equal to the number of particles. How many particles do we have? We have 3.01 times 10 to the 23. Divided by Avogadro's number. Avogadro's number is how many there are in 1 mole. And if you plug this into your calculator, you're going to get half. Okay? Plug this in, you're going to get 0.5. So this number of gold atoms is going to give us half a mole. And if we had half a mole of gold, how much gold do we have? Look at the atomic mass. The atomic mass of gold is basically 197. So if we had half a mole, we would have half of 197 in grams of gold. Okay? That's what that means. That's what that number represents. And one more example, these are all the same thing. They're just practicing the formula. So let's pick one at random. Let's do 14. How many moles of silver? And I'm skipping some of them because the rest are in there. You can practice with them if you want, but I'm not trying to make this presentation extra long. No, again, nobody likes watching 30-minute videos. How many moles of silver are there in a pure sample containing 1.5 times 10 to the 23 atoms of silver? So this is N. Okay, this is the number that goes here. And N day, this is the number that goes here. So just plug in 1.5 times 10 to the 23 into your calculator, divided by the 6.02. Plug that into your calculator and you get B. Okay. So this is a quarter mole. So this is 1/4 of a mole. Okay. Now, one more important piece. Okay. One more important piece is this. Okay. This part is not, in my opinion, essential. I'll go through it real quick. This is vocabulary, but I wouldn't give you these types of questions, but this is for your knowledge. When you hear the word molecule, it's referring to covalent compounds. So water is a covalent compound, and they're going to say water molecules. So if you see the word molecules, just know they're talking about a covalent compound. If you see the word formula unit, just know they're talking about ionic compounds. But that's not something you're going to see often. So I'm going to skip through this piece. Okay, I wouldn't call this section right here relevant. What is relevant, however, is this piece. Okay, this is the last bit. So when we've been talking about the mole thus far, we've been talking about elements. Okay, but you can also have a mole of a formula. Okay, so let's say we have salt. Okay, NaCl is salt. If you have 1 mole of salt, that means you have 1 mole of this entire thing. Okay, you have 1 mole of this entire thing. Okay. So before we start applying moles, let's recall that the little subscripts, this right here, tells you how many of that element you have in one of these units, in one of these formulas, or in one of these molecules. Okay. So in one water molecule, there are 2 hydrogens. In this one, there are 6 carbons. In here, you have 2 potassiums, okay? Why is that relevant? Why is that important? Well, let's say that we decided that we want 3 moles of table salt, okay? If we had 3 moles of table salt, I could ask you specifically, how many moles of sodium is that? So if we have 3 moles of table salt, which is 3 moles of this entire thing, how many moles of sodium do we have? Well, in one single salt molecule, there's only 1 sodium. So in 3 moles of table salt, I expect 3 moles of sodium atoms, okay? In water, let's look at the hydrogen. In one single water molecule, you have 2 hydrogens and 1 oxygen, okay? If I said that we had 6 moles of water, we now have 6 moles of water. How many moles of hydrogen do I now have? Well, in one single water molecule, there's 2 hydrogens, which means if I had 6 moles of the water, I have 12 moles of hydrogen, okay? This is where these values come in, okay? That's why I'm bringing this up, because you're going to see problems like that. And when you have that, all you do is you take the number of moles and you multiply it by the subscript, okay? That's essentially all you're doing. So this one doesn't have a number with it. Let's say, so right now in one of these, you have 6 carbons and 6 hydrogens. So if I had 1 mole of this entire thing, that means I have 1 mole of, or I means I have 6 moles of carbon and 6 moles of hydrogen. If I then decided I wanted 3 moles, I now have 18 moles of carbon and 18 moles of hydrogen, okay? So you can have a mole of a specific element, you can have a mole of a whole molecule, okay? The mole is applicable to a lot of different things, okay? That's the last important piece of information that you need to have, okay? And here they're going to go through the water example. So in 1 mole of water, you have 2 moles of hydrogen and 1 mole of oxygen, okay? Because in each water molecule, you get 2 separately and 1 oxygen. So if you break them apart, this is what you end up getting. And if you add up the masses, it's the same as the mass of the water molecule itself. So remember that when it comes to formulas, the mass is equal to just the sum of the atomic masses of all the different elements involved. So the atomic mass of hydrogen is 2. The atomic mass of oxygen is 16. Remember, it's here. So 16 plus 2 gives you 18 AMU, right? I told you that if you have 1 mole of something, you now converted this AMU to grams. So if we have 1 mole of water, that means we have 18 grams of water, right? If you split it up, you should get the same thing. So if we have 1 mole of hydrogen, that's 1 gram of hydrogen. But we have 2 moles of hydrogen, so that's 2 grams of hydrogen. Okay, so this is 2 grams. So this is 2G. And then if we have 1 mole of oxygen, that's 16G. And then 2 plus 16 is 18. Okay, so it's the same. Even if you split it up, you still up getting the same value. All right. So the mole can be applied to individual elements or it can be applied to entire molecules. Okay. That basically sums up the section. Okay. Now I'm gonna go through an example in the worksheet, and tomorrow we're gonna start talking about molar mass. That's what you guys have to look forward to. Okay, but that's it for today. So the important bits, the things I want to highlight, okay, is the two most important parts, in my opinion, is this, okay? A mole of something is just a quantity. This is just to summarize. So 1 mole is just this number. A mole is just a number, okay? A mole is just a number. This number is important because if you have that number of atoms, you then have the periodic table mass in gram form, okay? And that applies to formulas as well. So let's say NaCl. If I had 1 mole of NaCl, that means I have, this is basically 23, and this is 35 and a half. So I have 23 plus 35 and a half in grams of table salt if I have a mole of it, okay? It can be applied to individual elements or it can be applied to molecules, okay? And then the last bit that I find important is this, okay? And that is that if you have more than 1 atom of it in the formula, you need to multiply that by the number of moles to get the total amount, okay? Those are the important bits. Remember those and you'll be good. Okay, where are we right now? Wow, we're at 26. See, I didn't want to make this too long, but it is what it is. So the section we're working on today is the mole in Avogadro's number. So all the problems are going to be similar. They're going to ask you to either go from atoms to moles or moles to atoms, okay? So let's do an example of both. How many iron atoms are in 3 moles? So here we know how many moles we have. We want to figure out how many atoms we have, okay? So if you remember your algebra, okay, you just have to rearrange the formula. So the formula is N is equal to, it's an ugly N. N is moles, is equal to big N divided by Na. So what we're looking for is big N. This is what we're looking for. And so just rearrange the formula and you get that big N is equal to little n times Na. Okay, so this is what we're using for number 1. So we have 3 moles. So then big N is equal to 3 times Na, which is the 6.02 times 10 to the 23. And if you plug that into your calculator, you will get your answer. Okay, so plug in 3 times 6.02 times 10 to the 23, and you will get your answer for number 1. Okay, number 1, we're going from moles to atoms, so you have to rearrange the equation. And let's do one where we're going from atoms to moles. So here, then number 4. So that was number 1. We did number 1, and now I'm also going to do number 4. How many moles of neon are in this amount? So we know how many atoms we have. We want to find out how many moles that is. So N is equal to big N, which is the number of atoms. We have the number of atoms now. 7.53 times 10 to the 23. And then divide that by how many are in 1 mole, which is Avogadro's number, which is Na, which is 6.02 times 10 to the 23. Okay, this one I had a lot to talk about. Sorry for making this video kind of long. I was trying not to, but there's a lot of information. Okay, plug that into your calculator and you will get your answer. Okay, so that's how you do all of these. Okay, they're either going to ask you to go from moles to atoms or atoms to moles. Okay, and then number 9 and number 10 are just they're word problems. They're trying to confuse you a little bit, make life a little more challenging. But that's what you're doing for today. Okay. Thank you guys for your attention. I wish you all the best. Hope you guys are all doing decently. Okay, and enjoy the rest of your day.